In this video we present TimeClassifier, a visual analytics system for the classification of smart sensor data. In this video we present our system on data recorded from a penguin. We start off with an overview of the user interface. Firstly, we have a time series graph at the top. The user can select attributes to visualize in this view. The whole time series is shown. We can stack multiple attributes on top of each other with a separate graph for each. We can zoom in on the plot to show it in more detail and scroll across time. This is the traditional way biologists analyze their data. In the bottom left we have a search widget for searching for behaviours, and in the bottom right we have a classification widget which stores each behaviour group in a tabulated view. We can add a new behaviour to classify by clicking on the Add button. In this video we're going to be labelling ascent, descent, swimming and burst swim behaviours. As you can see, a unique categorical colour is assigned to each behaviour, which is used to reference the behaviour in our time series plot, as we'll see later on. We expose a manual labelling option in our system for the user to perform manual classification. The user firstly identifies a signal for a behaviour to classify. In this particular data we can see this subsection here corresponds to ascent. We apply rubber band brushing across the series and then cut the graph accordingly. Two vertical lines appear. These represent the start and end boundaries of a behaviour. We can double click on this region and drag and drop it into the appropriate classification tab, in this case ascent. Once we've dropped it into this view, we can see the segment then becomes red, which corresponds to the behaviour colour, and we now have the instance shown in our classification tab under the ascent. We now further add a descent behaviour. We cut the graph, navigate to ascent, double click and drag and drop into descent. The manual classification of data is a slow and time-consuming process. The behaviours of ascent, descent, swimming and burst swim are very repetitive throughout the signal. There are about 300 instances of each. We choose to apply our searching wizard utilising pattern matching to speed up the labelling process. The user can right-click on an instance to save a template in our database, or they can choose to search for it throughout the system. We select search and add ascent. We select not to resample the signal in this case and perform matching on the X, Y and Z components of acceleration. It's important to bear in mind that we can select any sensor channel to perform matching on. We select save, and we're then asked which algorithm to use for matching. In this case we use normalized correlation. The system goes away and performs the pattern matching on the signal. The results are returned almost instantly. Our template matching wizard is shown. Here the user is guided through refining a threshold value to verify, accept and reject matches. The user interactively modifies a threshold which has a direct impact on the signals extracted. The similarity value represents the percentage of how similar the pattern is to the template. 0 extract all matches, while 100% includes only an exact match. On the right hand view, we visualise all of the matches extracted overlaid on top of each other through the attributes of the template. The original template signal is overlaid in red. On the left hand view we have visualizations of where matches occur throughout the series. These are all aligned with an original plot of the time series. Firstly, we have a heat map. Here, yellow indicates low matches, whereas blue indicates areas of high matches. We then visualize all of the extracted matches and the distribution of matches via a histogram. As we lower the threshold, more matches are introduced. We keep lowering the threshold until we find a suitable value. In this case, we select 42%. We can see there are a number of outliers in the results view. We can use rubber band brushing to select lines to remove from each plot, as so. We can also reject matches on our visualization displays of where matches occur. In this instance, we know most of the matches occur in this region in the series. Once we are satisfied with the results extracted, we click Finish. The results are extracted into the results view in the bottom left. The extracted results are added to the results view in the bottom left. This features two further views. Firstly, a sparkline table view, where all results are shown in a tabular format, with each row corresponding to an extracted instance. We can inspect each of the signals individually and choose to accept or reject them using the buttons. By accepting a match, we choose which behaviour classification group to assign it to. In this case, we select Assent. We can see the signal has moved from the left-hand view and is now placed into the Classification tab. We can also go view and reject matches from this display. They are then removed from the results view. Additionally, we have an overlay view where we can further choose to delete matches and reject them from the view. Once we are happy with all the results in this view, we can select to move them all to the appropriate classification. The time series graph is then updated accordingly. We now inspect the time series to see how well the classification performed. We can see here the classification algorithm has missed an Assent behaviour. We can see the signal shape is a bit different to that of the other templates. We therefore choose to manually label this section. We can see otherwise the classification algorithm did fairly well. Otherwise, we would consider creating another template from this signal to perform matching on. We continue repeating this process of either manually labeling or searching by applying more templates until we are happy with the classification results and we've achieved the precision and recall rates we require.